Till now in the lectures that I have given, I have described solid state lasers and gas lasers, but in this following few lectures I will be talking about the semiconductor lasers, because semiconductor lasers form a very useful class of lasers and they are used in many aspects of everyday life. And they form a slightly different class of lasers because the energy levels associated with this laser, the semiconductor lasers, is not exactly the same as in a gas laser or the solid state lasers that I have been speaking of before. So, we want to know what kind of energy levels are possible in semiconductor lasers and how these energy levels can be utilized to get amplification of light. Okay. We have to just marry the energy levels to the amplification possibilities. Okay. And let us see how that goes. So, and what I want to tell you is I will be placing some facts and formula here which which are specific to the laser process or the amplification, light amplification process. Though a detailed study of semiconductors you may have already done in solid state physics class. Okay. So, I will not go into the detail of deriving any formulas, but I will be placing just the ones that are required for understanding of the lasing action. Okay. So, in all the other electrons, that occupy a semiconductor, okay, they share the entire volume of the material. See, again this is one big difference between the lasers we have spoken about before and the semiconductor lasers. So, we are talking about the electron states, okay, the quantum states that this electron occupies. Okay. And the electrons are all over the material, and the quantum mechanical wave function of all electrons overlap with each other. Okay. And so, you can see here the electrons will occupy can occupy states like this ones shown in red, and the green ones are electrons. Okay. Here they are shown as occupied, but many of these states can be empty, okay, at different conditions of the material. And electrons, by the way, are all fermions, okay, because they are like a swarm of electrons floating about in the semiconductor. So, it is like a electron gas, and they follow the Pauli's exclusion principle. And according to the Pauli's exclusion principle, the electrons cannot occupy the same quantum states. So, there are as many electrons as there are states. Okay. Again, this is a little bit different from the other lasers that we have spoken about. So, the kinetic energy of the electron gas increases with the temperature. Okay. So, once the kinetic energy of an electron increases, it will occupy, say, higher and higher states. Some energy levels are occupied which were vacant at absolute 0. At absolute 0, all these things may be all vacant, maybe just, and when the temperature is increased, okay, they start getting filled up. Now, how do I know how these electrons are getting filled up? Okay. That is given by the Fermi-Dirac distribution. The Fermi-Dirac distribution gives the probability that an energy level at an energy E, I have written E this way so that you do not get confused with E, which was given in previous lectures, and it related to the electric field. So, I will call it E, but okay, it is written this way, E will be occupied for an ideal electron gas in thermal equilibrium. So, my Fermi-Dirac distribution is giving me the the probability that the electrons will occupy these states. These states already exist and they may not be filled. At a certain temperature, they start getting filled, but how? They follow the Fermi-Dirac thing. So, the Fermi-Dirac distribution. So, f of E is equal to 1 of 1 by 1 plus e to the power epsilon minus mu k b t. T is the temperature, B is the Boltzmann constant which you have come across before. T is temperature in absolute degree Kelvin, energy state, and mu is again a energy state which we will describe later. For the moment, this is the distribution that is followed by the electrons when it has a little bit of energy due to the temperature increase, and that is how they will fill up all the states. Okay. Now, if I were to take a semiconductor, in totality, okay, and each of those atoms in the semiconductor are separated out and are isolated, they will have certain kind of energy levels. Maybe you can say something like this, the red ones. Okay. And each of those atoms and the electrons in those atoms will be able to fill up energy states of the same kind, similar kind. Each of those atoms. Now, those atoms are all isolated. They have this regular pattern of energy states like this. But once they come together, once all these atoms come together into this semiconductor formation, these energy levels split up due to the interaction between these atoms, the mutual interaction or interference between these atoms, and these energy levels just split up into something like this. And they split up and they form kind of bands. You can see this band, this band, this band, this band, and there are band gaps in between. You know, these are the band gaps where no electron can reside, no energy level is possible, nothing is possible here. These are all the energy levels here. This is a band gap, there is a gap in the bands, and here. So, some of these bands may be called valency band, and some of this band are called the conduction band. Okay. And in between nothing is possible. Okay. So, it is a gap. Okay. So, now we know what this semiconductor structure looks like, structure in terms of energy looks like. And the electrons, of course, are moving about in that whole system, and they occupy, these things show the occupation of states by the electrons. This is not, this is also electrons. Okay. There are some in the conduction band, some in the valence band, and these are also all the bands that are, the electrons are occupying all these states. Okay. Now, let us see what is the finer or the details of these energy bands, what these energy bands look like exactly. Okay. Okay. So, I have to describe the energy levels. Okay. How do I get to these energy levels? Okay. An electron of mass m is confined to a length L, and there is an infinite barrier. Okay. And the solution to the wave equation for a system of one electron, I have just taken a one dimensional case now. One dimensional case, the boundary conditions are given by psi n 0 is equal to 0, and psi is the wave equation which is the solution to the Schrodinger's equation. Okay. And this is giving me the boundary condition. Psi is the wave is the solution to that equation. Okay. So, psi n 0 is equal to 0 corresponds to, say, this point. Okay. And psi n L is also 0, which corresponds to this point. Basically, by a one dimensional case, what I mean is the electron is confined to a length of L. So, electron cannot leave this length. If it comes to 0, the electron, it sees a big barrier. If it comes to L, it sees a big barrier. Okay. So, these are the conditions that the boundary conditions that you need to put in the Schrodinger equation and solve it and find the solution or find the wave that is a solution to the Schrodinger equation. And the wave is, for this one dimensional case, it is a sine like wave. Okay. So, the wave is A, which is the amplitude sine of 2 pi lambda n by x, lambda n by x. Okay. So, it is a sine x, it is a sine wave, where half of n, lambda n is equal to L. N is an integer. Okay. Do not confuse this n, though I am repeating it again. We had called it till now n, we had depicted as the refractive index, but here it is just an integer 1, 2, 3, 4, 5, 6 like that. Okay. So, here for n equal to 1, it is exactly like this, it is half a wavelength, therefore, L is equal to lambda by 2. Okay. When I go to the next energy level, it becomes twice n is 2. So, this is a full lambda, this is a full wavelength, and the next energy level is this, it is 1 wavelength plus half a wavelength. Okay. So, these are all the energy levels that are described. Sometimes they call these things orbitals. Orbitals is almost the same as an energy level. Now, what is the value of these energy levels? The value of these energy levels is given by E n. N is depending on n is equal to 1, 2, 3 like that. H cross square upon 2 m pi n pi by L whole square. Okay. So, this is the energy levels in case of a one dimensional case. That means the electron is confined between 0 and L, it is just moving between 0 and L, and the possible energy states are given here by E n. But then we are not always interested in the one dimensional case, but in analogy you can always find the solution to the 3-dimensional case. In the 3-dimensional case, the electron is in a box or a cube with edges L. So, it is a 3-dimensional box, all the edges are the same L, and the electron is confined in that. So, we want to know what kind of wave satisfies these boundary condition and how Schrodinger's equations solution looks like. So, that solution, it looks like this. Okay. Psi k, k is a wave vector, okay, and psi k r is equal to, r is in directions, different directions, exponential I k dot r. Okay. So, this is my solution. Now, what are the energy levels associated with this kind of a wave? That is what I am interested in. So, there is a lot of derivation here, but you may have already done it in your solid state physics class. So, at this point, just recollect all those derivations and come to the final solution which is given here. Okay. So, I am interested in knowing what are the energy states. Okay. So, the energy states given here in a 3-dimensional case is this E is equal to h cross square k square upon 2 m. Now, k is a vector, k is a vector, and it has components kx square plus ky square plus kz square. So, the energy is given by all this, and k takes the value of 2 pi by L. See, it is analogous to this n pi by L. It is analogous to this one dimensional case, okay, but this is in 3 dimension k, and q p q r takes 1, 2, 3 these integer values. So, you have the k values are known, the components of the total k here, this k which is a vector. Okay. Once you know that, you know the energy levels. H cross is anyway reduced Planck's constant. 2 m is the mass of the electron. Okay. So, you know all the energy levels, and that is what we are looking for. Once you know the energy levels, you know how the electrons will occupy these energy levels, and then the transition from those levels will give you give you the photon that you are looking for, or give you the lasing action that you are looking for. So that is the aim of finding the different energy levels. Now, let me go to this. Okay, if you have noticed, just see this E is equal to h square k square upon 2m. Okay. This is an equation of a parabola, all right. This is, so these energy levels are, it is following this parabolic equation. Okay, if you just recollect, just put down here the equation of a parabola. Y is equal to ax square plus c. Okay. C is a constant, A is also a constant. Okay. A is a constant to be seen what it is, C is a constant. We will see what it is like here. For this moment here at this point it is not showing any C. Okay. So, this is the equation of a parabola. So, the energy states are, I should say, parabolic in nature. So, this is the energy band diagram of a semiconductor, and it is a parabolic band. It is called as a parabolic band because of the kind, the formula for the energy states. Okay. So, here this is the parabola. The valency band is also a parabola. It follows this equation. In case of valence band, this is the equation that is followed. Okay. Just notice these two are a bit different. This is EC plus h cross square k square upon twice mc. mc is the mass of the conduction electrons, the electrons in the conduction band, and mv is the mass of the holes actually, or the electrons in the valence band. Okay. So, E is equal to EV minus, here this is plus, so the parabola looks like this. Here EV is equal to minus, so it will come onto the other side like this. Okay. And if you notice this parabola is slightly wider, slightly opened out, while this parabola is even more opened out than this, almost a flat line. Okay. This parabola has this sort of an opening, and this parabola has a lesser kind of a larger kind of opening. Okay. These two are different. Now, so one is a conduction band and one is a valence band. And if you notice this EC, that is energy in the conduction band of the lowest most conduction band. These are all in the higher most conduction band, and EV is the energy of the highest energy band of the valency band. Okay. This is the lowest and this is the highest energy. Okay. Now, if you have noticed one more thing, I had in my previous slide, I had talked about the mass of the electron here, m. Okay. Now, in this slide I write mass here. It is with a C because it is called the effective mass. mc is the effective mass of the electron in the conduction band, and energy of the valence band, and effective mass of the hole mv is given by this. Okay, this is a negative structure, that is why you get this. Okay, mv, and mc is the electron in the conduction band. So, I have something called the effective mass. just to give you the concept of effective mass. The electron has a mass, okay, that is the end of the story. But then why do we need to think about the effective mass here in case of semiconductors? Okay. That is because it gives you an idea of how the electrons are moving in the semiconductor under the influence of some external forces. Now, what are the external forces? It could be the periodic potential within the semiconductor, or it could be a potential given by an electric field externally. So, we want to know how those how these electrons in the conduction band, or how the holes in the valence band, how are they moving in such a situation? Are they mobile enough? So, this effective mass gives you an idea of the mobility of these electrons. Okay. If they are highly mobile, that means their electron mass is reduced. So, they are able to move more easily, or are their mobility not so much, are they inert? Okay. So, if they are inert, then again the effective mass is different from the actual mass. Okay. So, this is the whole idea of effective mass. Okay. Now, if you see the effective mass formula is given by h cross square d square E by d k square raised to the inverse of that. Okay. This is the effective mass. So, so if you see this function, this is a function E k in terms of k. This is a vector k. Okay. So, and this is E, it is a function of this k, which is a parabola. Now, d square E by d k square, mathematically it gives you the rate of change of dE by dk. Okay. But the rate of change of dE by dk actually gives you an idea of the curvature of this structure, or curvature of this band. Okay. dE by dk gives you a curvature of this band. So, depending, and then at the inflection point, which is the inflection point? This is the inflection point. dE by dk, the work of dE by dk is to give you all these quantities. So, and it tells you, how steep is this. If it gets steeper, suppose this is getting steeper, then your effective mass is becoming lower and lower. Okay. And if it is becoming lower and lower, that means the electron is able to move further into under the influence of, say, an external electric field. I will just show you what I mean by steeper. Steeper of this. By steeper I mean, okay, this parabola is getting like this from something like this. Okay. So, in this case the effective mass will be less, in this case the effective mass will be more. Actually, that comes out even from the equation of a general equation of a parabola. Okay, here. This is a general equation of a parabola. So, this A part, okay, if it is larger or smaller, depending on that, the steepness of the parabola goes up or comes down, okay, depending on that factor A. And that is exactly what is happening even here. The factor A here is, say, if I just mark it a little bit, this part is that factor A. Okay. So, depending on this factor A, your parabola is becoming steeper or not so steep. So, depending on that. So, that is the idea of effective mass. Okay. Now, at a finite temperature, suppose at absolute 0 degree Kelvin, everything here is empty, this, all these energy levels are empty, but everything is filled in the valency band. Suppose there is a little bit of temperature, just have a look at this. Some of them, close by may just jump into this part, okay. And some of them remain behind, and then what is left behind is a hole. It shows as a hole. There is a hole here, there is a hole here, there is a hole here because all the electrons have jumped up here at a finite temperature. Okay. It may be also that some at a room temperature, some of them may be here and they have gone up here. Okay. So, so you have to see this. When you give an electric field, again the kinetic energy increases and the electrons just jump up from the bottom to the hole. So, this is how the semiconductor works. At this point, I think I should tell you that in case of an insulator, this gap is very, very large. This gap is very large, maybe around 3 electron volts. So, when it is around 3 electron volts, the electrons are unable to overcome this gap and jump into the conduction band. Okay. So, this remains, the conduction band remains empty, while the valence band remains full. In case of suppose at room temperature, the electrons just need an energy of about a few milli electron volts to jump into the conduction band. But then my conduction band gap is 3 electron volts. Okay. So, the electrons cannot jump. So, that becomes an insulator. But if say I have increased the temperature by some means, or no, I haven't increased, I am just saying my band gap becomes less. Band gap is less than 2 electron volts, much less than 2 electron volts. Then what happens is, some of these electrons can jump into this band very easily, even at room temperature. Okay. If that is the case, then it is a semiconductor. If the band gap is more, it is an insulator. If the band gap is small, then it is a semiconductor. So, I just gave you an idea of what a semiconductor energy structure looks like. In the next lecture, we will go ahead with the kind of absorption and emission that are taking place between these bands, and which leads to the formation of stimulated emission or leads to the formation of amplification.